Now that we understand how workloads are deployed and operated in the AWS cloud, it's time to focus on something absolutely central to everything you build in AWS: compute. Compute is what actually runs your applications. It's where code executes, where requests are processed, and where business logic lives. In AWS, compute isn't just one service, it's a set of flexible options, each designed for different types of workloads, performance needs, and operational models. In this task, we're going to learn how AWS provides compute through multiple service categories and, most importantly, how to choose the right one. We'll start by looking at Amazon EC2, which gives you virtual servers in the cloud. Here, you'll see that not all instances are the same. Some are designed for heavy CPU workloads, others for memory-intensive applications, and others for high-performance storage. Understanding when to use compute-optimized, memory-optimized, or storage-optimized instances is a key cloud practitioner skill. Then, we'll move into containers, where AWS offers managed options like Amazon ECS and Amazon EKS. Containers let you package applications and dependencies together, making deployments faster and more consistent. We'll talk about when containers make sense and how they differ from traditional virtual machines. After that, we'll explore serverless compute, such as AWS Lambda and AWS Fargate. With serverless, you don't manage servers at all. AWS handles provisioning, scaling, and availability, while you focus only on your code. This model is especially powerful for event-driven workloads and modern cloud architectures. Finally, we'll connect everything together with one of the most important cloud concepts: elasticity. You'll see how auto-scaling allows compute resources to grow and shrink automatically based on demand, one of the defining advantages of cloud computing. By the end of this section, you won't just recognize AWS compute services, you'll understand why AWS offers so many options and how to choose the right compute model for each scenario you see on the exam. And in the real world? Let's start by breaking down AWS compute services, one category at a time. All right, let's start with the two most common EC2 instance families you'll see on the CLFC02 exam: general purpose and compute optimized. The goal here is simple: match the workload to the resource it needs most: CPU, memory, storage, or networking. 1. General purpose instances. Balanced. Think of general purpose as the default choice when your workload needs a balanced mix of CPU, memory, and networking. Nothing is extremely heavy in one direction. When to choose general purpose. Use these when you describe your app like this: it's a normal web app. It's an API server. It's a microservice. It's a dev/test environment. It's a business application backend. Common families you'll hear about: T-Series, T2, T3, T4G equals burstable performance. Best when CPU usage is spiky, quiet most of the time, then bursts. Example: a small website that gets traffic peaks during certain hours. M-Series, M5, M6G equals steady, general workload baseline. Best when you want consistent performance for typical production apps. Example: an application server running all day with predictable load. Exam tip: if the question sounds like a typical server and doesn't emphasize high CPU or huge memory, general purpose is usually the best answer. 2. Compute-optimized instances. High CPU. Now, compute-optimized is for workloads that are CPU-bound, meaning the main bottleneck is processing power, not memory or storage. What CPU-bound means in practice. These workloads do a lot of calculations, encoding/decoding, intensive request processing, fast, repeated compute operations. When to choose compute optimized? Use them when the question hints high CPU utilization, compute intensive, needs powerful processors, low latency processing, lots of math, simulations, rendering, encoding. Common families: C-series, C5, C6G, C7G, equals compute optimized. Great for sustained high CPU performance. Examples: batch processing jobs, video encoding, high-performance web servers, ad serving, gaming servers, scientific modeling. Exam tip: if the scenario screams processing power, choose compute optimized, C family. If it screams balanced app server, choose general purpose, T or M family. Quick memory trick for the exam: T/M equals typical, mainstream apps. C equals compute equals CPU heavy. Now let's move on to 2EC2, instance categories that are designed for specialized, high-performance workloads, memory-optimized instances and accelerated computing instances. These are not general-purpose servers. You choose them when a workload has a very clear technical bottleneck, either memory or specialized compute hardware. 3. Memory-optimized instances. Memory-optimized instances are built for workloads that need to hold and process large amounts of data directly in memory. In these scenarios, CPU speed is not the main concern. The real performance gain comes from having a lot of RAM available, so applications don't constantly read from disk. R-series, R5, R6G, R7G. These are the most commonly used memory-optimized instances. They are ideal for high-performance databases, both relational and NoSQL, where fast and memory access is critical. X-series, X1, X2. These provide extremely large amounts of memory and are typically used for enterprise-grade, in-memory workloads such as SAP HANA. U-series. These are bare metal instances with multi-terabyte RAM, designed for very large enterprise applications that require maximum memory capacity and direct hardware access. Typical use cases include in-memory databases, large caching layers, big data analytics engines like Apache Spark or Hadoop. Exam tip: if the question mentions large datasets in memory, high-performance databases, or in-memory analytics, think memory optimized. 4. Accelerated computing instances. Accelerated computing instances take performance a step further by using specialized hardware accelerators instead of relying only on CPUs. These instances are designed for workloads that can run much faster in parallel or require hardware-level acceleration. P-series, P3, P4D. These are GPU-based instances optimized for machine learning training, deep learning, and high-performance computing simulations. G-series, G4, G5. These focus on graphics-intensive workloads such as video rendering, real-time graphics, and machine learning inference. F1 instances. These use FPGAs, allowing customers to implement custom hardware acceleration for very specific workloads. Typical use cases include machine learning and deep learning, HPC simulations, video transcoding, graphics rendering and visualization. Exam tip: if you see keywords like GPU, machine learning, deep learning, graphics, or hardware acceleration, the correct answer is accelerated computing. To summarize, If your workload needs a lot of RAM, choose memory-optimized instances. If your workload needs GPUs or specialized hardware, choose accelerated computing instances. AWS provides these instance families so you can match the infrastructure to the workload instead of over-provisioning or wasting resources. So far, we've looked at general purpose, compute optimized, memory optimized, and accelerated computing instances. Now let's finish this topic by focusing on workloads where storage performance or extreme compute coordination is the primary requirement. 5. Storage optimized instances. Storage optimized instances are designed for workloads that need very fast access to large amounts of local data. These instances prioritize high disk throughput, low latency, high IOPS, input/output operations per second. They typically use local NVMe storage, which is directly attached to the host and delivers extremely fast performance. I-Series, I3, I4. The I-Series is built for high random I/O performance. Ideal for workloads that frequently read and write small pieces of data. Extremely low latency. Very high IOPS. Best examples: NoSQL databases like Cassandra, MongoDB. Real-time analytics. Transactional workloads that hit disk constantly. D-Series, D2, D3, DIN. The D-Series focuses on dense storage and sequential access. Large amounts of storage per instance, optimized for streaming data rather than random access. Best examples: data warehouses, Hadoop and big data clusters, distributed file systems, log processing systems. Exam tip: if the question emphasizes large datasets plus disk performance, especially with local storage, think storage optimized. 6. High-performance computing, HPC, optimized instances. Now let's talk about high-performance computing, or HPC. This is not just about fast CPUs, it's about how instances communicate with each other. HPC workloads are tightly coupled, require very low network latency, often involve thousands of nodes working together. HPC series, HPC 6A, HPC 7G, these instances provide extremely high network bandwidth, low latency inter-instance communication, optimized networking for cluster computing. Best examples: scientific simulations, weather forecasting, financial risk modeling, molecular modeling, and physics simulations. Key distinction for the exam: compute optimized high CPU per instance. HPC optimized high-speed communication between instances. Summary: the key to choosing the right EC2 instance type is identifying what resource your workload depends on most. Balanced workload general purpose, CPU, heavy compute optimized. Memory heavy, memory optimized. Specialized acceleration accelerated computing. Disk I/O heavy, storage optimized. Large, tightly coupled clusters, HPC optimized. On the AWS exam, the question almost always tells you the answer. You just need to listen for the dominant requirement. Containers on AWS. Now let's talk about containers on AWS. One of the most important modern compute patterns you'll see in both the AWS exam and real-world architectures. Containers allow you to package an application together with everything it needs to run, code, libraries, and dependencies, so it behaves the same way across environments. AWS provides fully managed services that cover the entire container lifecycle, storing images, running containers, and orchestrating them at scale. For the Cloud Practitioner exam, you should clearly understand 4 core services. Amazon ECR, AWS Fargate, Amazon ECF, Amazon EKS. Let's start with the foundation. 1. Amazon Elastic Container Registry, Amazon ECR. Amazon ECR is where your container images live. Amazon ECR is a fully managed container image registry, compatible with Docker and OCI standards. Before you can run containers, you need a secure place to store and manage the images, and that's exactly what ECR does. Key points to understand. You push images to ECR after building them. ECS and EKS pull images from ECR when running containers. ECR integrates tightly with IAM for access control. Important features: private and public repositories, image scanning for vulnerabilities, lifecycle policies to automatically clean up old images, native integration with C/CD pipelines. Exam tip: if the question mentions storing, versioning, or scanning container images, the answer is Amazon ECR. 2. AWS Fargate. AWS Fargate is about running containers without managing servers. Fargate is a serverless compute engine for containers. It works with both Amazon ECS and Amazon EKS, and its key value is simplicity. With Fargate, you do not manage EC2 instances. You don't worry about patching, scaling, or capacity planning. You pay only for the CPU and memory your containers use. Why teams choose Fargate? Ideal for variable or unpredictable workloads. Faster to deploy and operate. Strong security isolation, each task or pod runs independently. Exam tip: if the question says, run containers without managing servers, or serverless containers, the answer is AWS Fargate. Now that we've covered where images live, ECR, and how to run containers serverlessly, Fargate, let's talk about orchestration, managing containers at scale. 3. Amazon Elastic Container Service, Amazon ECS. Amazon ECS is AWS's native container orchestration service. ECS is a fully managed container orchestrator designed specifically for AWS. It lets you define how containers run, how many run, how they scale, how they communicate. Key characteristics: deep integration with AWS services, IAM, ALB Cloud. Watch. Simpler operational model than Kubernetes. Can run on EC2 or Fargate. ECS is a great choice when you want tight AWS integration. You don't need Kubernetes portability. You prefer a simpler learning curve. Exam tip: if the scenario emphasizes AWS native container orchestration, the correct answer is Amazon ECS. 4. Amazon Elastic Kubernetes Service, Amazon EKS. Amazon EKS is AWS's managed Kubernetes service. EKS allows you to run Kubernetes on AWS without managing the control plane yourself. AWS handles Kubernetes upgrades, control plane availability, security patches. Why organizations choose EKS? Kubernetes portability across clouds, existing Kubernetes expertise, complex, multi-cloud, or hybrid strategies. EKS can run on EC2, more control. On Fargate, less operational overhead. Exam tip: if the question mentions Kubernetes, pods, clusters, or multi-cloud portability, the answer is Amazon EKS. Let's tie everything together. Amazon ECR, Think store container images. AWS Fargate. Think run containers without servers. Amazon ECS. Think AWS native container orchestration. Amazon EKS. Think manage Kubernetes on AWS. Key exam pattern. If AWS wants simplicity and AWS integration, choose ECS plus Fargate. If AWS wants Kubernetes compatibility, choose EKS. If the focus is image storage, choose ECR. Before we talk about specific services, let's clarify what serverless compute means in AWS. Serverless does not mean there are no servers. It means you don't manage them. With serverless compute, AWS takes full responsibility for provisioning servers, scaling capacity, maintaining availability, and handling infrastructure failures. You focus only on your application logic, and you pay strictly for what you use. For the AWS Cloud Practitioner exam, there are two primary serverless compute options you must understand: AWS Lambda, AWS Fargate. And the key skill is knowing when to use each one. 1. AWS Lambda, event-driven serverless compute. Let's start with AWS Lambda. AWS Lambda allows you to run small pieces of code, called functions, in response to events, without provisioning or managing any servers. You upload your code, define what event should trigger it, and AWS handles everything else: scaling, execution, and availability. How Lambda works. Lambda is event-driven. It runs only when triggered. For example, a file is uploaded to Amazon S3. A record changes in DynamoDB. An HTTP request comes through API Gateway. A scheduled event runs every hour. Billing model. You pay per request and per millisecond of execution. If your function is not running, you pay nothing. Lambda is ideal when your workload is short-running, event-based, stateless, and highly scalable. Common Lambda use cases: automatically resizing images when users upload photos, processing streaming data in real time, building serverless REST APIs with API Gateway, running background jobs like cleanup tasks or notifications, automating operational actions such as responding to CloudWatch alarms. Exam tip: if the question mentions events, automatic scaling, pay-per-execution, or no servers to manage, Lambda is usually the answer. 2. AWS Fargate, serverless containers. Now let's talk about AWS Fargate. AWS Fargate is also serverless, but instead of running functions, it runs containers. With Fargate, you don't manage EC2 instances, clusters, or scaling groups. You simply define how much CPU and memory your container needs, and AWS runs it for you. How Fargate works. You run containers using Amazon ECS or Amazon EKS. You specify the CPU, memory. AWS provisions and scales the compute automatically. Billing model. You pay for the CPU, memory, only for the time the container is running. When Fargate is the right choice, Fargate is ideal when your application is already containerized. You need a full runtime environment. Your workload runs longer than typical Lambda functions. You want serverless benefits without rewriting your app. Common Fargate use cases: running microservices in containers, processing batch jobs that take minutes or hours, lifting and shifting existing containerized applications, running APIs that require full control over the runtime. Workloads with variable or spiky demand. Exam tip. If the question mentions containers, ECS, EKS, or no EC2 management, think Fargate, not Lambda. 3. Other serverless style, AWS services, context awareness. While Lambda and Fargate are the main serverless compute services, AWS also offers other services that follow the same serverless principles. Examples include Amazon's 3. Serverless object storage. Amazon DynamoDB, serverless, NoSQL database. Amazon Aurora serverless, auto-scaling relational database. You don't provision servers, you don't manage capacity, and you pay only for usage. These services reinforce the serverless mindset, even if they are not compute engines themselves. Summary: Lambda versus Fargate. Let's summarize this in exam-ready terms. Use AWS Lambda when the workload is event-driven. Execution time is short. You want fine-grained, per-request billing. You don't need a full OS or container runtime. Use AWS Fargate when the workload is container-based. You need more control over the runtime. The application runs longer. You want serverless benefits without managing EC2. In one sentence, Lambda is best for functions triggered by events, while Fargate is best for running containers without managing servers. That distinction alone answers many AWS exam questions correctly.
Thank you for watching. See you in the next class.